Hey guys, so today we're going to be doing probably the most important lesson in all of physics in grade 10, but it's also a really long one, and there is a couple of really important calculations. So make sure that you're writing down the examples that we go through or trying them on your own, and let's get into it. So this lesson is all about different types of energy in physics. We're going to be going over different types of potential energy and kinetic energy. We are going to be doing calculations with certain types of kinetic and potential energy. Specifically, the most important ones are gravitational potential energy and mechanical kinetic energy. And then at the very end, we're going to go over some total mechanical energy problems. So when a system has energy, that just means that it has the ability to work. If you remember in, I think, the last lesson, we talked about how work is just energy being transferred to an object. So energy is a scalar quantity, so it has a magnitude or an amount of energy, but not a direction. Anytime there is an energy change that is taking place, you're going to see this as either a physical change in the object, a chemical change taking place, like a chemical reaction, the motion of an object changing, or the shape of an object changing, or the temperature changing. There are two different categories of energy. We have potential energy, which is stored energy or positional energy, and then kinetic energy, which is always energy of motion. And then the total mechanical energy of an object is just its potential energy plus its kinetic energy. So these are all of the different types of potential and kinetic energy that we're going to be going over. We have chemical energy, gravitational energy, nuclear energy, spring energy, and electrical energy as examples of potential energy. And then for kinetic energy, we have the mechanical kinetic energy, rotational energy, electromagnetic energy, sound energy, thermal energy, and electrical energy. And you may notice there that electrical energy is under both categories. It is a different type of electrical energy under both of those categories. For each one of these types of energy, you will have to know its description, and then for a couple of them, there's also some calculations to go along with that. So chemical energy is the potential energy stored in the chemical bonds between the atoms of a molecule. So we kind of touched on this a little bit when we were doing our lesson on the leaf in the last unit, one of those plant lessons, where we talked about the fact that when glucose is made during photosynthesis, the energy is stored in the bonds of that glucose molecule. And energy can be released or taken in whenever bonds are either broken or formed. We can measure the chemical potential energy of a substance by combusting it in a calorimeter. So essentially you just like burn it and see how much energy that requires. Essentially when you burn this, the more chemical energy in a compound, the hotter your combustion is going to be, and then you just measure the heat of the combustion by heating up water using that. By the way, when you like read the package of like food, and then you have like the nutritional facts, the calories are the amount of chemical energy that is stored in that compound, in the food. Gravitational energy, this is energy that is stored in an object due to the height of that object and the force of Earth's gravity. So the higher an object, the more gravitational energy it has. When it is resting on the ground, for instance, and it does not have the ability to fall any further, the gravitational energy is zero. As soon as an object is above ground level and has the potential to fall, then it has gravitational potential energy. Weight is the amount of gravitational force on an object, which is measured in newtons. It is mass times the acceleration due to gravity, which is 9.81 meters per second squared. That number, 9.81, is very important for a lot of your calculations, so lock that in. And then mass is the amount of matter an object has. It is measured in things like grams or kilograms, stuff like that. So remember, weight and mass are not the same thing. Mass is what we are actually talking about when we say how much something weighs. Weight is measured in newtons, and it is the downwards force on something. Okay, so as we talked about in this one, weight is just mass times the acceleration due to gravity, which is g. So if I said, what is the weight of a 7.2 kilogram mass on the Earth's surface, we would just take 7.2, multiply it by 9.81, and that would be our answer. Okay, you can try the second question on your own there. In that case, you're plugging in mass and weight and solving for your G value. Okay, this is one of like the two most important formulas that we're going to deal with in this entire unit. This is when we calculate gravitational potential energy. So the formula is EPG equals mgh. EPG is just the potential energy due to gravity, or gravitational potential energy. And the M is the mass of an object, must be in kilograms. So if you're given the mass of an object in, say, grams, you do have to convert it to kilograms. And then the G is the acceleration due to gravity. As long as we are here on Earth, it is going to be 9.81. And then H is the height above ground level, must be measured in meters. So let's try some practice questions for this. Okay, so for the first question here, it says a 2 kilogram textbook is lifted from the floor to a shelf 2.1 meters above the floor. What is the gravitational potential energy of the book relative to the floor? So we're going to use our formula, EPG equals mgh. We will plug in our mass of 2 kilograms. Our G value is 9.81. And the height is 2.1 meters, and we'll just multiply those all together. So 2 times 9.81 times 2.1 equals 41.2, and energy is always measured in joules. Then it says, what is the book's potential energy when it hits the ground? So if at the very top, where the shelf is, it had 41.2 joules. As it drops, it is going to be losing gravitational energy, because the higher something is, the more gravitational energy it has, until it hits the floor or the ground or whatever, at which point it will have 0 joules of energy left. Okay, pause here for a moment, try the second example on your own, and then come back for the answer. So for the second example, we're still going to use the same formula, and then we were given the mass of 2.5 kilograms, but this time we were given the amount of gravitational energy, which was 300 joules. And then of course we use our 9.81 as our G value, and we're going to be solving for H. So the first thing I did was multiply my M and my G together, which gave me 24.525 times H. In order to get the H by itself, we divide by that to cancel it out. What we do to one side, we must also do to the other. So 300 divided by 24.525 gives me about 12.2 meters. And that would be my final answer. Okay, next up we have nuclear energy, which is a type of potential energy stored in the nucleus of an atom. And nuclear fission and nuclear fusion are the two ways that we can release some of this nuclear energy. So it's through nuclear reactions that we can release nuclear energy. Nuclear fission is the type of nuclear reaction that happens in like nuclear power plants, also happens at the center of our Earth. And this is when you take an atom, a large atom, usually like uranium or plutonium or something, and you split it into smaller atoms. So you're actually splitting the nuclei of the larger atoms into a whole bunch of smaller atoms. Nuclear fusion is the type of nuclear reaction that occurs in stars, including the sun. This is when you take the nuclei of smaller atoms and fuse them together to create a larger nucleus. Then we have spring energy, which is energy stored in an elastic or spring. This happens anytime you move the elastic or spring out of its resting position. So if you stretch a spring or an elastic or compress it, you are giving it the potential to move. Because as soon as, if I say like stretch an elastic, as soon as I let it go, it's going to snap back. So when it's stretched out, it has spring energy. When I let it go and it snaps back, that would transform into kinetic energy because it would be moving. Same if I like compress a spring. When the spring is compressed, it has spring energy. As soon as I let it go, it would transfer spring energy into kinetic energy. And then electrical energy. Like I said, this can be both potential or kinetic. The electrical potential energy is the energy stored in a difference of charges. So if you have two differently charged objects next to each other, that difference in charge is going to result in potential energy. And the bigger the difference in the charge, the more potential energy it is. This is essentially what we have in a battery. So if you just have a battery sitting there, you have a positive end and a negative end. That difference in charge between the positive end and the negative end is electrical potential energy. Electrical kinetic energy is the energy from moving electrons. So again, kinetic energy is always something moving. In this case, it's going to be electrons. And that happens when you have essentially a wire that electricity is passing through. So if you take that battery that we were talking about and you connect a wire going from the negative end to like a light bulb to the positive end, just like a little simple circuit. As soon as you attach the wire and complete that circuit, electrons will start to flow out of the negative end of the battery through the wire towards the positive end. And so that movement of electrons through the wire is what is your kinetic electrical energy. So we can calculate the amount of electrical kinetic energy, which is the electrical energy, again, that is flowing through a wire. And the formula is electrical energy is equal to power times time, where energy is, as always, measured in joules, power is measured in watts, and time is measured in seconds. So let's try some of those practice questions. Okay, so for the first question here, it says how much energy does a 60-watt light bulb use in 30 minutes? So again, this needs to be in watts and seconds. So the first thing you're going to want to do is take your 30 minutes and multiply it by 60 in order to figure out how many seconds we're dealing with here, which is 1800. And then we just plug it into our electrical energy formula. Take our power, which is 60, multiply it by 1800. And you get 108,000 joules, which you could also write as like 1.08 times 10 to the power of 5. Okay, try the second one on your own and then come back for the answer. Okay, so for the second problem there, you should plug in your joules where the electrical energy is, plug in your 4,500 seconds and solve for P, by dividing away the 4,500, do the same to the other side, and you get 0.4 watts. Okay, so now we are talking about different types of kinetic energy, not just potential energy. So thermal energy is the kinetic energy of molecules in motion related to temperature. So essentially, the higher the temperature, the more molecules will move, or the faster that they will move. So what we say is the thermal energy is higher when the temperature is higher. And that is because thermal energy is just the kinetic energy of the molecules based on their temperature. Sound energy is also kinetic energy. This is when molecules vibrate in unison. As you may be aware, the way that we hear things is when sound waves travel through the air and then cause vibrations in our inner ear, middle and inner ear. So the faster that molecules vibrate, the more kinetic sound energy that they will have. And usually that includes higher pitched noises. So higher pitched noises tend to have more kinetic energy. Then we have electromagnetic energy, which is the kinetic energy found in the waves of electromagnetic radiation, which includes waves of all the different types of radiation found on the electromagnetic spectrum. So radio waves, microwaves, infrared radiation, all the different colors of visible light, UV radiation, X-rays, and gamma rays. The higher the frequency of the waves, the shorter the wavelengths, the more electromagnetic energy they will have. Just so you guys know, when it comes to the electromagnetic spectrum, you do need to be able to order all of these different types of radiation from highest to lowest energy, or lowest to highest energy. You do also need to know the relationship between frequency, wavelength, and energy, which is, again, higher frequency has shorter wavelengths, has more energy. Another way of saying that is that lower frequency and longer wavelengths have lower energy levels. The L's all go together. So this is what this would look like. So the highest energy has the shortest wavelength. This is also where we would have the highest frequency, which when we're talking about frequency, we're just talking about the number of wavelengths that can fit in a certain space. So if you give yourself like a centimeter on this electromagnetic spectrum, at the high energy level, you might be able to get like 1, 2, 3, 4 wavelengths in a centimeter of space. If we go to the low energy side, you can only get like 1 wavelength in there. So that's a frequency of like 4 compared to a frequency of 1. So high frequency have short wavelengths, but a lot of energy. Long wavelengths, so wavelengths that take up a lot of space, have lower frequencies and lower energies. So from highest energy to lowest energy, we have gamma rays, X-rays, UV rays, visible light, which is down here, infrared, microwaves, and radio waves. You do also need to know the order of visible light from high to low or low to high. So the highest energy visible light is violet. It is right next to ultraviolet on the spectrum. So it goes ultraviolet and then violet, and then blue, and then green, and then yellow, and then orange, and then red. And red is right next to infrared. So essentially, if we're going from high to low energy, it's like Roy G. Biv backwards. If we're going from low to high, it's Roy G. Biv forwards. But you should notice I did not use the word indigo. Indigo does not actually belong on the electromagnetic spectrum. It has been removed because the electromagnetic spectrum is only supposed to include the primary and secondary colors. Indigo was added for like political reasons and has since been removed for scientific reasons. So do not put indigo on your electromagnetic spectrum. Okay, next up we have rotational energy, which is the kinetic energy of a rotating object, so anything that's like spinning, and the faster it is rotating, the more rotational energy it has. Then we get into the mechanical kinetic energy, which is the second super important type of energy calculation that we're going to be doing, the first being the gravitational potential energy. Mechanical kinetic energy is just the energy of a moving object, so that's like falling or sliding, based on its speed and its mass. And of course, it's measured in joules. This is sometimes also referred to as translational energy, but for our purposes, we're going to be calling it mechanical kinetic energy. Essentially, the heavier an object is and the more speed that it has, the more kinetic energy it will have. So this is the formula that we're going to be using. MEK equals half the mass times the velocity squared. So the EK portion, or the MEK, is just the mechanical kinetic energy. The mass is the M, once again, must be in kilograms. The speed is in meters per second. And then, of course, it needs to be squared. So let's try some practice calculations. Okay, so for the first question, it says a shot putter heaves a 7.26 kilogram shot with a final speed of 7.5 meters per second. What is the kinetic energy? So I'm just going to plug in the mass of 7.26 and the speed of 7.5. Then I am going to do the 7.5 squared. So the rest I'm just not going to touch for a second, times 56.25, which is 7.5 squared, and then just multiply these all together. So 56.25 times the 7.26 times 0.5 gives me 204.19 joules, would be my final answer. Okay, try to figure out the next two on your own. So pause here for a moment and then come back to the answer. Okay, so for question number 2, I'm going to plug in my joules where the kinetic energy is. I still have my half. My M is what I'll be looking for, and I plug in my speed of 965 squared. First step, according to BEDMAS, is to do the exponents. So my 965 squared is 931,225. Then I multiply that by the half to get 465612.5, and of course keep my M. And then to isolate M, I divide by that on both sides. I end up with 0.00859 kilograms as my mass. Yeah. Okay, last but not least, we're using the same formula. We're plugging the joules in where the MEK is, plugging in my mass of 16 kilograms, and this time we're solving for the speed. So I start by doing a half, or 0.5 times 16, which is 8. Then in order to get it away from the v squared, I divide by 8 to cancel it out. Must do the same on the other side. 920 divided by 8 is 115. And then in order to get to the v by itself, I do need to square root it. So my final answer is going to be whatever the square root of 115 is, which is 10.72. So that is in meters per second. That would be my speed. Okay, so total mechanical energy we already briefly talked about. It is just the kinetic energy of an object plus its potential energy. So it is just the total sum of all of the different types of energy that an object has. So for example, if you throw a ball upwards, it is going to have kinetic energy because it is moving upwards, and it will have potential energy because it is not at ground level. Same with anything that's falling. Anytime something is falling, it has kinetic energy as it moves downwards, and it has the potential energy of whatever its height above ground is. Usually energy is constantly being converted from one type of energy to another. So for example, kinetic energy being converted to potential or potential energy being converted to kinetic. Anytime you have an object that is falling, you always have potential energy being converted into kinetic energy. The further down something is, the lower its potential energy is, but the longer it has fallen for, the more kinetic energy it has. Energy is never lost or gained as long as you have a closed system. And for all of these calculations that we're going to be doing, we're going to assume that we have a closed system. So what that means is that we're assuming that we're not losing energy to forces like friction and air resistance. Even though that's not usually the case in real life, that's what we're going to be assuming for this year. So the total amount of energy of an object will always stay the same, even if the types of energy are changing. Okay, so for instance, if you have an object that is like sitting on a shelf above ground level, at the top here, 100% of its energy is going to be our gravitational potential, our EPG. By the time it hits the ground, as we've talked about before, it is going to have 0 of its energy being gravitational. However, right as it hits that ground, 100% of its energy is kinetic. And so at any point through this fall, that conversion is happening. Right around here, it might be 75% gravitational and 25% kinetic. Further down, we might have the inverse of that, where it's only 25% gravitational and 75% kinetic. So throughout this entire fall, the energy is being converted from potential energy into kinetic energy, but the total amount of energy doesn't change. If we had 100 joules of energy to start off with, we would have 100 joules of potential energy and no joules of kinetic energy. And then as we fall downwards, as that ball falls downwards, that energy gets converted from potential to kinetic until we have 100 joules of kinetic right when that ball hits the ground and no joules of potential energy left. We will do a couple practice questions talking about how this conversion happens today, and then we'll get kind of more in depth into it and do some more practice questions about it in the next lesson. Okay, so this question says the potential energy of a skier as they go down a hill is 30,000 joules and the kinetic energy is 20,000 joules. Where does the kinetic and potential energy come from, and what types of energy are they? So the kinetic energy that we're talking about here, so for question number 1, the kinetic energy is going to be your mechanical kinetic energy, and it just has to do with the movement of the skier down the hill. Meanwhile, the potential energy that the skier has is gravitational potential energy, EPG, and it has to do with the height of the skier up the hill. How much further down can it go before it can't fall any further? What is the total mechanical energy? Well, that is just going to be our 30,000 joules plus our 20,000 joules. So it is 50,000 joules of total mechanical energy. And then it says, as the skier goes over a big jump, the potential energy increases to 36,000 joules because the skier is gaining height again. What is the kinetic energy at that point? So again, we know that the total energy doesn't change, and we just found out the total energy is 50,000 joules. So if I just do 50,000 joules minus the amount of that is potential energy, whatever's left over must be my kinetic energy. So 14,000 joules would be kinetic energy at that point. Okay, next up, the question says a 0.2 kilogram frisbee is tossed horizontally 1.5 meters off the ground at a speed of 6 meters per second. What is the total mechanical energy? So I know that the total energy is just the kinetic energy plus the potential energy. In this case, the kinetic energy is mechanical kinetic, so that is half mv squared, and the potential energy is gravitational, so mgh. And you could certainly solve these separately and then add them, or just solve it all together like I'm about to. So I'm going to plug in the mass of 0.2, my speed of 6, still a mass of 0.2, g is 9.81, and h is 1.5 meters. Oh, don't forget to square your speed. So 1/2 times 0.2 times 36 plus 2 times 9.81 times 1.5 is 29.43. 0.5 times 0.2 times 36 is 3.6 plus 29.43 plus 29.43 is 33.03 joules of energy in total. Okay, try the next question on your own. So pause here and then come back. Okay, so for the second question, we're given that the ball is 0.8 kilograms, that when it is 20 meters off the ground, it has a total mechanical energy of 2,000 joules, and it wants to know its kinetic energy. So I'm going to plug in the 0.8 kilograms as well as the 20 meters off the ground, multiply those, plus also multiply my 9.81, and get 156.96 joules of gravitational energy. I then know that my total energy is 2,000, so I will just subtract the amount of that is gravitational. Whatever's left over must be kinetic, so 1,843.04 joules of kinetic energy. Okay, this last page of practice here is more similar to what we're going to be doing in the next class. So this is kind of an introduction to that based on what we've already talked about. So the first question, it says a 1.3 kilogram bucket of paint falls off the top of a ladder from a height of 8.2 meters. At what speed does it hit the ground? So because what I have to start off with is mass and height, I am going to start first step with my EPG formula, since that is the only formula that I have that uses both mass and height. So I'm going to do 1.3 kilograms times 9.81 times 8.2 meters. And I get 104.57 joules. Now, the next part is a little bit tricky because it's asking for the speed that it hits the ground at. And so what you have to remember is what we were talking about here, that whatever the gravitational energy is at the top where this object starts off, 100% of that gravitational energy is going to be kinetic energy by the time the object hits the ground. So because this is asking for the speed that the object hits the ground at, what I can do is take that potential energy I just calculated and plug it in as the kinetic energy when the object hits the ground. So my next step is going to be to use my MEK equals half mv squared formula, plug this in where my MEK is, plug in my mass of 1.3, and I'm going to be solving for speed. And the only reason that I can plug this in here is because, again, I know that by the time the object hits the ground, all of this gravitational energy has been converted into kinetic energy. So next up, 1/2 or 0.5 times 1.3 is 0.65. I, of course, divide to get my v squared by itself. So 104.57 divided by 0.65 is 160.88. And then, of course, square root to get the v totally by itself. So the square root of 160.88 is 12.68 meters per second, would be my final answer. Okay, so for the last question here, we have a 1.2 kilogram weather balloon falling from the sky. It says halfway through its descent, it has a speed of 618 meters per second. It wants to know the height that it falls from. Again, we're going to look at what units we have, and based on that, figure out what formula to start with. So even though it's asking for height, we're going to kind of ignore that, go with the mass and the speed that it gives us, plug those into our MEK formula, so half mv squared. I just did this all at once, got 229154.4 joules. And then I'm just going to plug that into where my EPG is, plug in my 1.2 kilograms again and my 9.81 to solve for H. So I multiply those two numbers together to get 11.772. Divide on both sides, that gives me 19,466 meters as my height. The only thing we have to remember is that this is the height halfway through the descent, because that was the speed halfway through the descent. So we just multiply it by 2 to figure out what height the descent actually started at. You will get 38,932 meters. Okay, so for more practice with all of these different types of things, see this last slide here. I've broken it down into questions on the different types of forces, gravitational potential energy calculations, mechanical kinetic energy calculations, and then the total mechanical energy calculations, which involve both potential and kinetic energy. Okay, that is it for today. We will continue kind of building on this energy conversion thing in the next lesson.